uniform rod PQ has length 2L and mass M. It is free to rotate about a horizontal axis through P perpendicular to its length. It is released from rest when PQ is horizontal. Find the angular speed when PQ is vertical. Okay, what we're going to do is first we're going to calculate the moment of inertia of a rod rotating through P. So it's a axis perpendicular to the plane of the board. It's going into the plane of the board and it's rotating downwards. Okay, so it's a preset formula that IP is 4/3 ml cubed. It's taken directly from your notes. Okay. Now, what we got to do next is that we got to define what's called a standard position. Standard position is where this body has no potential energy. Okay, so what we can do is, where's the center of gravity of a rod? Dead center, isn't it? So when this rotates down, its center of gravity ends up here. If we say that this is h equals 0, this is where it has no potential energy left. Okay, so it's a good idea to use that. We're going to use the conservation of energy. PE plus KE, P1, KE2 equals PE2 plus KE2. Now, in this circumstance, there's no real linear kinetic velocity. All the kinetic energy is in the form of a turning motion. Okay, so what we're going to do there is we're going to replace that with mgh1 for potential energy 1 plus a half inertia times its angular speed squared, then mgh2 plus a half I omega 2 squared. Which variable do we want on its own by the end of this equation? Can anybody tell me? Angular speed when P is vertical? We want the angular velocity of the second one. That's our goal right there. Get that W2 on its own. Okay? So, going to do next is mgh1. How far is it above the axis, guys? Anybody? L. Okay, because it's a length 2L, which means it's length L. Length P is L from the center of gravity, and then another L to the bottom. So we say is mgl plus. Is it moving at the start? It's not moving at the start at all, so it's 0 for that one. And then mgh2. What's its potential energy at the end? 0, because it hits rock bottom. It's right here. Its center of gravity is on the h equals 0 line. So we'll put 0 there. 0 here, and then a half. What's our I value? We got it earlier. 4/3 ml cubed. Multiply by omega 2 squared. Okay. Turns that into 2/3 ml cubed. Ends up to be mgl. Okay, the m's cancel. One of the l's cancels. We're going to get a 3g over 2 equals L squared. L equals the square root of L squared sorry guys, at the very beginning, not ml cubed, ml squared, excuse me. So that was ml squared, so it means that L cancels with that there. It's just L, not L squared. My fault. Then bring the it's L, and then there's the omega 2 that I forgot there at the end. Bring the L underneath. So we're going to get omega 2 squared equals 3g over 2l. Therefore, omega 2 on its own is the square root of 3g all over 2l. That was a very bargain basement conserving energy. You didn't have to use the perpendicular axis term. You didn't have to use the parallel axis term. All that changes in question 7. Okay, so some of the harder ones we were looking at earlier in the exercise. So a uniform rod PQ has length 4L and mass M. The point Q is attached to the circumference of mass M and radius L in such a way that P and Q are collinear. Okay, collinear would mean something like this. I'll do the circle first. Specify a center of the circle. Disk length L, and to the center of the disk radius L. Now it's attached to the disk. It's 4L from here to here. Are we happy enough with that? And then it's going to be a so the attachment point is from the rod to the outside of the circle is the 4L. It's attached to the circumference, not attached to the center of the circle. It's attached to the circumference of the circle. Okay, so that's why I'm saying the attachment is there. This here, however, is of length L. Okay. Find the moment of inertia of the system about an axis through P perpendicular to the plane of the disk. Now, where is P? P to Q. So what's happening in effect is that it's going to rotate this way, and then by the end of the picture we're going to be down this way here. Everybody got that? We're rotating down that way. Okay, because we're going through P. Now let's work on this. So the generic formula for the rods is I equals 4 over 3 ml squared. What size is that for? That's for a length of 2L and a mass of M. How does my system differ? It's 4L, which means it should be twice, the L value is twice as big. So what I'm going to do is for the rods, its rotational inertia, its inertia around P is going to be 4 over 3 M times 2L to be squared, because it's twice as large. That's going to get me 16 over 3 ml squared. Okay, just quick adjustment on the formula there. Okay, now we work on the disks next. Where does the disk rotate around? Our generic disk formula is a half mr squared. What does that refer to, the half mr squared? Huh? Refers to rotating in this little axis here, and the disk is rotating this way around its center. Is this axis parallel to P? P is going this way. The axis through here is going this way, like a CD player threaded on the axis. If you want your 3D point of view, in effect, the axis I'm talking about now goes straight through the center of the disk. That's my half mr squared. And the axis we're talking about, P, is through this way. We can see that they're actually parallel axes. Okay, so our job is going to be parallel axis theorem very soon. Okay, because they're already in line with each other, they're parallel to each other. There's no need for the perpendicular axis theorem. It's a non-runner this time. Now, let's have what's the dimensions of our disk? Mass M, radius L. This formula here is for mass mass m, radius r. So it's very simple. The discs, we'll call it C. The discs IC, rotation around its center, is a half ml squared. Next thing we're going to do is the parallel axis theorem. Now, anybody remember the parallel axis theorem? IP equals IC plus MD squared. Okay, still working on the disk. Okay, so what do I put down for IC? A half ml squared. How far is it away from the P axis? Anybody? 5L. It's 4L plus L. You can see it up there. So it's going to be m times 5L squared. Then we're going to add the two of them together. We should get 51 over 2 ml squared. Now, what we got to do is find the total inertia. I total, which is equal to this one here plus this one here. And what you'll get there is 185. 185 ml squared all over 6. Okay, now that we have our information for our inertia of our system, we just got to quickly go back to our original diagram. Not like that, we won't. Okay, and yeah, here's one of them. And then I'm going to draw a second diagram down here. Now, you got to determine yourself a good place to say where is the basically where's a good place to say that potential energy equals 0. Okay, that's what you got to decide. So that's the two of them there, and that's P. Okay. Can anybody take a good guess at where you think potential energy equal to 0 might be a good idea? Which center of gravity is going to be the lowest? The rod center of gravity or the disk center of gravity by the end of the question? The disk center of gravity is clearly lower. So what we're going to do is we're going to mark this as h equals 0. Okay. So try and get that there. H equals 0. That's L. That's another 2L, and that's a 2L to the very top. Okay, we're going to now do the conservation of energy. You got to break them up individually into their individual parts. So this is what's referred to as a compound body. It's made up of a rod and a disc. When we're doing the conservation of energy, we got to take both the rod and the disc into consideration because of the different locations of their center of gravities. Okay, so going to write down here is MGH1, that's for the rods. MGH1 referring to the disk, plus a half IW squared referring to the system's inertial energy. Okay, and that will equal MGH2 for the rods, MGH2 for the disk, plus finally a half IW2 squared 2, and that'll be 2, 1. Okay. All right, let's begin. What is the rod's potential energy at the start of the question? The rod weighs mass m. Okay. How far above the ground is it? Sorry? 5L. Did I do this one? Sec. Oh. One adjustment, guys. There it is there. Vertically above P. See the language vertically above P? Just have to make one adjustment with my my diagram here, okay? Nothing particularly too wrong about it. Just need one adjustment. Okay, see if we can drag them all down as a unit. There we go. Perfect. Okay. What it wants me to adjust this to is that it's actually starts vertically above. So it's actually this way. Okay. So it's still falling this way, but it's going from here all the way to down here, because it says vertically above, not starting horizontally. Okay. So I just had to make that quick adjustment. Still the same thing. The standard position's still down here. Okay, where is the center of gravity of the rod again now? Now we have to calculate a new distance above the ground. That's another 2L. And this here is L. We should have made that diagram so big now, but we'll work with it. Okay, let's start with the mg. How far is the rod's center of gravity above the ground? L, 3L, 5L, and 7L. Do you see it there? This is the turning point, and that's the start of the rod above it now, and you can see that its center of gravity. I'll just highlight the center of gravity. That's the center of gravity of the rod at the start of the question. The second highlighted part is the center of gravity of the rod at the end of the question. Okay, so how high is the center of gravity at position 1 above the ground? 7L. mg times 7L. What about the disk? The disk is another 3L above that, isn't it? So it's going to be 10L. You can see the gap here from the rod center of gravity to the disk center of gravity is an extra 3L. Okay? So what we're going to get is mg 10L. Okay? And after that, does it have any spinning energy at the start of the question? Any inertial energy? No. It's not moving, so it's a 0. At the end of the question, how far is the rod's center of gravity above the standard position of h equals 0? 3L. So mg 3L for the rod. The disk is on the center, is on the h equals 0 line, so it has no potential energy. And that finally leaves a half. The I value of our system, which we said is, I value of our system is 185 ml squared over 6. And then that's times the, that is times the angular velocity squared. Okay, now we're here. Anything cancel both sides? Suppose we could go after the m's, couldn't we? Maybe next time. M. The L's as well. L. Okay. I see 7g plus 10g to give me 17g. On the other side, I see 3g. This thing here is going to be 185 over 12. 185 over 12. L omega 2 squared. Okay. Bring the 3g over to your side, and what should we get? 14g. Okay, would somebody do me the favour of bringing the 185 over 12 over the other side, turn it upside down, so it's going to be 12 times 14g all over 185. Okay, somebody tell me what that is. What's it? 168 over, and the L on the bottom. So it's going to be 168 over 185. Square root that. W squared equals 168g over 185 L. That's rotational energy at the end of the question. Okay? We all good with that? Alright. Now, Question A. The diagram shows a rectangular lamina of mass m, length 6L and width 3L. A point mass is attached at K, point mass over here, and the system is free to rotate about a horizontal axis through P. System is rotating in the plane of the board, which means the axis of rotation is going into the board. Is that okay? So what we're going to do is a quick diagram underneath here, just to quickly explain what's going on. Grab yourself a rectangle, clone said rectangle. Okay, so if I mark its spin, where it spins from, what we're going to be looking at is something like this. So spins from this, oh dear, spins from this point here, and it falls down to this point here. Okay, where's the center of gravity of a rectangle? Center of gravity of a regular rectangle? Anybody? If you were to draw, you could do it this way. You know that the center of gravity would come dead center. Okay, or you could just bisect both sides and two axes. Now, there you go. Okay, there's a problem with this one. Okay, let's denote the letter C as the center of gravity of the rectangular lamina. Anything you're given in your notes regards the moment of inertia of a rectangular lamina. All these planes, okay, all the planes in question, they're parallel to the axis, or sorry, they're parallel to the plane, not perpendicular to the plane. So in effect, if you were to draw something like this, that's to represent it in 3D. Okay. In effect, your axes go this way and this way here. And what you want to do is you want to find a perpendicular axis that I will denote in red, and you want to find the perpendicular axis. Does that make sense to everybody? You have to first find the perpendicular axis that goes through the center of the lamina, not the horizontal axes, okay, which is on the which is a flip across, flipping the page over its own in its own plane. Okay, that's what you gotta find. Once we find that, we then transfer it to the end. We use the parallel axis theorem, and we then create a second moment of inertia that's around the parallel, around the axis through P. That was meant to be in green, but you get the gist, right? So everybody see what we got to do there? Got to find both moments of inertia. We'll call this one we can just call them two different things. We'll call this one IA. We'll call this one IB. And then we're going to follow that up with IC using the perpendicular axis term. Then, once we get that, we're going to find out what IP is by using IC plus MD squared, otherwise known as the parallel axis term. That's how we're going to do this question, just a matter of doing it. Okay, so let's go back up here and let's find out what it is. Any lamina, its I is 1/3 ml squared. This works for a system of mass m and length 2L. Okay, let's start off with IB. IB is this one here. It has a length of what's it, 6L, yeah? So what does that mean for its formula? IB. So I'll just root this out for a second. So can anybody predict what IB is going to be on its own? IB, a third m 3L squared, which is going to get me 3ml squared. Okay? By the way, my A and B is the opposite to the solutions. Okay, they're just random letters. They don't have to. They could be one way or the other way. Okay, IA guys. A third m, and what's the length this direction? 3L over 2. So it's going to be 3L over 2 squared. And then once you do that, you're going to get 3 over 4 ml squared. Okay, once we're completed that, what's the next step then? We have IB, we have IA. What's the next step after that? Anybody? Use the perpendicular axis theorem to find out what IC is. So, perpendicular axis theorem is IC, as I said, IC equals IA plus IB. Add the two of them together. You can see them plain as day right there. That one and that one together. Add them together and we get IC equals 15 over 4 ml squared. Somebody just verify that for me. Okay. Now we know what IC is. Now finally, IC is the red axis. It's parallel to this blue axis that I'm drawing through P. I can now use the parallel axis theorem. Whole point of the question is to find the system rotating around P. Okay. So IP equals IC plus MD squared. IP ends up to be 15 over 4 ml squared plus. Now, how far is IC away from IP? Any guesses? 3L. So we're talking about 3L here. So it's going to be M times 3L squared. IP therefore equals 51 over 4 ml squared. That's your system. That's your total answer for your rotation as shown here around the axis P perpendicular to the plane of the board, or the plane of the actual planes. Okay. Now, what system do we use when we're talking about before and after pictures? Oh, we left one thing out, didn't we? There was one last thing there. We left them out. This guy here, guys. Where is he located? Need a new colour. Use blue. The point mass, guys. Okay. So the lucky thing about the point mass is located here. The one good thing about the point mass is that its inertia is already parallel. So we just have to get it and then use the what's that? It's md squared. Okay. What we can do with the point mass, guys, is it's just mr squared. We don't have to worry about what direction it's going in. So regards point masses, and this is always the case for point masses, is that we don't have to worry about what axis they're going through. In general, they're always going parallel to the axis we're talking about. Okay, so point mass is automatically just add on an md squared onto our system. So point mass md squared, and how much weight is the point mass? mass m. And how far away is the point mass? Point mass is going to be 6L away. So 6L squared, which gives me 36 ml squared. Add this is just the rectangle. So add the moment of inertia around P of the rectangle to the moment of inertia around P of the point mass. 36 ml squared plus 51 over 4 ml squared. And that will give me 195 I total of 195 over 4 ml squared. Okay. Okay, guys. And okay, we start fresh now. There we go. Okay. Now, center of gravity of the rectangular lamina is signaled in green. Okay. The point mass is signaled in purple. By the end of the question, which one has the lower position? Which center of gravity has the lower position? The lamina or the point mass? Point mass. What do we do with that position then? We call it the h equals 0 position. Okay. And from here to here, guys, how big is that? 3L. Okay. 3L. And that's another 3L up to here. Okay. Let's do the usual system. Everyone knows the system now. P1. You have to do both of them individually. So you're going to have the potential energy P1 of the rectangle, the point mass, the inertial energy of the system. That's the KE equals P2 of the rectangle. So P2 of the rectangle. You're going to have the potential energy of the point mass, and then finally the kinetic energy of the system. I have IW2 squared KE. Reread the language of the question. What exactly does it want me to do? Find the speed. Okay. Does that specify angular speed or just regular speed? It's going for regular speed. Okay. Alright, guys. It's going for regular speed. We're gonna find omega. Omega is the angular velocity, not the actual velocity. So, anybody remember from circular motion what we do with this? Phi equals R omega. Remember, when you're rotating at a radius distance at an angular velocity of W, your actual velocity is directly proportional to the radius. Example, two kids in a a merry-go-round. The kid that's closer to the center, while you're moving at the same angular velocity, the kid that's closer to the center is actually moving slower than the kid on the outside edge, because the radius affects the velocity. So phi equals R omega at the end of the question. Reason being, it says speed, it doesn't say angular speed or angular velocity. Okay? So we're going to make that adjustment at the very end. Okay, let's begin. How far is the rectangle's center of gravity above the ground? Or the lamina? mg. How far? Red dot? 6L. The point mass, how far is that above the ground? It's also 6L. Does it have any speed at the start of the question? Any speed? 0. What's the rectangle's potential energy at the end of the question? mg 3L. The point mass is potential energy at the end of the question? 0, because it's on the h equals 0 line. And then finally a half. What was that big massive inertial number we got? 36 ml squared. Oh, sorry, 195 over 4. Times omega 2 squared. Okay. 12 mgl. Take away 3 mgl gets me 9 mgl. 195 over 8 ml squared omega 2 squared. Okay, gonna have to work this down a wee bit. We're going to get cancel the m's, cancel one of the l's. 72g over 195 L equals omega 2 squared. Just simply get rid of the squared sign, square root the other side. Okay. Does 72 over 195 break down to anything different? Can somebody check me? So what is it? 72 over 195? Sorry? Does it break out to 24 over 65? Sorry? This one's breaking it up differently, isn't it? So look, we can just leave it anyway. It's no big deal if we don't break it down that little bit more, alright? Now, what's its speed then? Phi equals r omega. What is the radius from the point of rotation? The point of rotation being this big blue dot here. And our fastest point. Now, which point does it specify? Does it specify the point mass? It wants the point mass's velocity. So how far is the point mass away from the center of rotation? The distance between the two blue dots. Anybody? 6L. So, it's going to be phi equals r omega. Phi equals 6L multiplied by 72G over 195L. Okay.